Hello, everyone. My name is Ahmad, and I would like to welcome you to this talk on our work on automatically repairing defects in hardware designs. So let me start by motivating the problem that we're trying to address here. Not only is it that the bugs in software or hardware are very difficult and time consuming to fix, but also these bugs can actually end up costing companies millions if they're not caught and fixed in time. This is especially true of hardware, but it is really impractical to deploy bug fixes once the device has been manufactured and then subsequently shipped to the consumers. One proposed solution to this problem in the software engineering community is addressing the use of automated program repair, which aims to fix bugs in the program while preserving the desired functionality. For APR for software, we typically start with a faulty program with some bug and then a test suite that has at least one failing test case that exposes the bug. The first step in software APR is fault localization, where we perform some sort of analysis on the program to implicate lines of code that are likely responsible for the bug. And this step is actually crucial to the success of APR because it serves to narrow down the search space for the program repair algorithm to then apply fixes from. Once fault localization has narrowed down potential sources of the bug, APR then tries to apply a patch to the program and then tries to validate the patch, tries to see if the applied patch actually fixes the defect. Eventually, the program repair loop terminates when either a correct repair is found or the allocated resources have been exhausted. And then we would like to be able to do something similar for hardware. However, there are two major reasons why the years of research on software APR has actually not been applied to hardware yet. First off, software level APR uses test suites to guide the search for repairs, and it is not immediately applicable to the hardware test benches without some technique to bridge this gap. Let me demonstrate this idea in a bit more detail. Here we have this test suite for a program with, say, 8 test cases, 2 of which fail. A super basic fitness function for this program repair could assign this candidate program a fitness value of 0.75, which is like 6/8. Fitness values like these are used to guide the search for repairs. And then when you pass all test cases, you are done with the APR loop. Hardware test benches, however, work very differently. There are usually no discrete passing or failing test components. Instead, a test bench typically simulates the device under test for some specified duration of time, and the developer can then monitor the values of the output at certain time steps. Taking this example output from the simulation of a basic 4-bit counter with some overflow bit, it is not important to understand here what these output wires correspond to. The key bit here is, given a simulation result, how do we assign a fitness value to this candidate design? Remember, we need such fitness values to guide the search for repairs beyond just random searching. So that's problem number 1. Problem number 2 is that fault localization techniques from software APR just do not scale to hardware. And this is a major problem because, as I mentioned earlier, fault localization is absolutely critical to the success of APR. So traditional fault localization approaches from software typically start with a faulty program with a test suite with passing and failing test cases. It then uses information about the lines visited for passing and failing tests to produce a ranked list of suspicious lines likely contributing to the bug. However, the problem is that hardware designs are parallel in nature. You can think of it in terms of all the code is running all the time. And this means that such fault localization approaches are just not applicable to these parallel hardware descriptions. Well, let me introduce you to CirFix, a hardware design-focused APR algorithm that solves the 2 problems I went over by introducing a novel data flow-based fault localization approach for hardware designs, and then also a new hardware domain-specific approach to guide the search for repairs. And then, spoiler alert, CirFix actually fixes hardware defects with repair rates similar to that of established software-based techniques, indicating that our approach is effective at bringing over the benefits of software APR to this new domain. How do we do this? That is precisely what I'll dive into for the remainder of this talk. So I begin my talk with some background related to hardware designs and then automated program repair, and then briefly introduce CirFix. The rest of this talk will focus on the methodology behind CirFix, and then I'll present our experimental setup and results, and then later part with some concluding thoughts. Right, so I mentioned earlier that traditional hardware test benches do not admit observations externally to any external entity, right? Like a fitness function for such fitness calculations to be computed, unlike fitness functions for software level APR. So to bridge the gap between software APR and hardware designs, we introduce our novel fitness function that is tailored to this hardware domain. At its core, the CirFix fitness function evaluates the acceptability of some program variant by assigning a value ranging continuously between 0 and 1 to the variant, where 1 indicates a correct repair. And then our fitness function actually operates on two key insights: visibility and comparison. Let's look at visibility in a bit more detail. What's important to note here is that the output values from a test bench, a hardware test bench, are usually not made available or made visible to some external entity. For our purposes, this would be a fitness function to measure how good or bad a candidate repair is based on its behavior during simulation. As such, we propose a general method of instrumenting the test bench for the design code to record the values of output wires and registers for certain time steps during the design simulation. A screenshot of what such instrumentation may look like is shown on the slide. Essentially, we have a forever block that executes as long as the simulation is running. It waits for a rising edge that is a high state of the clock wire, upon which it writes the values of counter out and overflow out, the two outputs of the circuit, to a file. That is basically all there is to the instrumentation process. Notably, we do not make any changes to the testing logic of the bench. Once we have the output values recorded by simulating a circuit using our instrumented test bench, we then move on to the comparison phase of our fitness function. As a reminder here, we desire a fitness function that assigns high fitness values to candidate repairs that display behavior similar to that associated with, say, a correct implementation of the design. As such, we have the CirFix fitness function perform a bit level comparison of the recorded output against some developer provided oracle to sum up the level of bit matching between the simulation and the simulation output and the actual oracle. The slide shows the formula for how such a fitness function and the total possible fitness could be computed, focusing on the fitness sum alone. The formula takes as input the simulation output and the oracle. It then sums over all k time steps during a simulation, and then for each time step, it loops over all of the n output bits for that time step. For every 0-1 bit match, it adds 1 to the fitness score. For every such mismatch, it takes away 1 from the fitness score. And then we also have an additional weight of phi associated with bit matches or mismatches for Verilog values of x or z, which indicate uninitialized and high impedance respectively. Note that the underscore here represents essentially a value of 0-1. It's a don't care bit. So, and the formula for the total fitness works in a similar way. So I'll not go over it in the interest of time, but overall we find that our fitness function is then highly effective at rewarding incremental changes to a circuit's design code that brings the design closer to repair. And I'll show this later for our research questions as well. All right. So let's now shift gears and talk about addressing the second problem highlighted at the beginning of my talk, fault localization. As I mentioned earlier, traditional fault localization approaches from software API are just rendered inapplicable to these hardware descriptions that are parallel in nature. This is where novel fault localization for hardware designs comes in. At a high level, the CirFix fault localization approach produces a uniformly ranked set of implicated design code for a faulty circuit. Our approach starts with the abstract syntax tree for the circuit design, the output from simulating the circuit, and then also a developer provided oracle for expected circuit behavior. The first step in our algorithm is to produce a set of output wire or register identifier names that have a mismatch between the simulation and the oracle. This step is very similar to how output values are compared for the fitness function, so I will not go over it in the interest of time. And then the next step is using this mismatch set to perform a fixed point analysis of assignments made to output wires and registers. This is where the bulk of the fault localization work lies, and I'll go over the step in detail in the next slide. And then following the fixed point analysis, the CirFix fault localization approach produces a uniformly ranked set of implicated AST nodes that are all likely contributing to the bug. That's basically how our fault localization approach works. Focusing a little bit more on the fixed point analysis, where I said the bulk of the work lies, on this slide, we have the high-level algorithm for our proposed fault localization approach. We start by initializing fault localization and this mismatch set to empty sets on line 1, and then we obtain an other set, mismatch prime, using this get output mismatch function that I described earlier in the previous slide. And this function basically returns a set of wire or register names that have output mismatch. And then the while loop on line 3 is where the fixed point analysis is performed. Essentially, while our mismatch prime and our old mismatch are not equal, we continue to loop through lines 4 through 11. And then for each node in the AST, we check to see if the node is implicated by our mismatch set. There are essentially two ways for a node to be implicated. either the node represents an assignment to some mismatched output variable. Like for example, if count was incorrect, if count is being assigned a value of 1, it could be wrong. So that's one way to get implicated. And then the other way of getting implicated is essentially if the node represents a conditional that includes a mismatch set. For example, if we have this conditional, if reset equals 1, and then you assign a value to count, it is possible that an incorrect value of reset assigned an incorrect value to count. So those are two ways for implication to happen. But then for any implicated node, we add the node and then all of its children to the fault localization set. Additionally, if a child of an implicated node is itself an identifier node, that is, it's a wire or register name not already part of the mismatch set, we add the identifier name to the mismatch prime set. This step is important for transitively capturing data and control dependencies, starting from our original output mismatch and then working our way up to see where else the problem might lie. Once there are no new wires or registers added to the mismatch prime set, the algorithm then terminates and then returns the fault localization set computed so far. And that's how our fault localization approach works. We find this approach is fairly effective at precisely implicating potential sources of the bug, as we'll later demonstrate for our experimental results. And then there are also other parts of our methodology included in the paper text that I will actually skip here in the interest of time, but I encourage you to go read the paper if you are interested. All right, moving on then to the experimental results phase of this talk. To evaluate the efficacy of CirFix, we needed a benchmark suite of defect scenarios for hardware descriptions written in Verilog. A defect scenario consists of a base circuit design, an instrumented test bench for the design, a developer-provided oracle for the circuit behavior. This is only the real. This is the only real human cost to the CirFix framework, and then also a design defect for the circuit under consideration. However, we found that companies are not willing to give away their circuits or design defects, usually due to IP concerns, and as such, we decided to go with the defect seeding approach that is sometimes seen in the realm of software. To obtain these expert seeded defects, we then first had to select hardware projects to include in our benchmark suite. The first 6 projects in our benchmark suite correspond to projects from intro-level VLSI courses. They're meant to be indicative of repairing a smaller individual component inside a circuit design. The remaining 5 projects are indicative of repairing large circuit designs monolithically. The first 4 of these projects are taken from OpenCourse, which is the leading website for open source hardware designs. And the final project is an open source project taken from GitHub. To see defects into otherwise correct implementations of the hardware projects, we recruited 3 hardware experts, 2 from industry, 1 from academia, and then we instructed them to seed 2 categories of defects. Category 1, which is easy. These defects include the kinds of mistakes, say, pertaining to simpler high-level aspects of circuit design. And then category 2, hard defects. And these defects are more complicated usually, and they usually require more effort to diagnose, understand, or fix. And then in total, we obtained 32 defect scenarios from our experts, and we make this benchmark suite publicly available for future hardware repair approaches to be evaluated on. For our experimental study, we wanted to investigate 4 things, but I'll only really focus on 3 here in the interest of time, and I encourage you to read the paper for the 4th one. First up, we really wanted to know what is the repair rate of CirFix? Is CirFix actually effective at repairing hardware defects? The second question we wanted to investigate was CirFix's performance for these individual defect categories, easy versus hard. We also wanted to investigate the quality of the CirFix fitness function. And then finally, we wanted to investigate the sensitivity of CirFix to the quality of the expected behavior information. For this last research question, I encourage you again to read the paper, but as a spoiler here, we found that CirFix is not overly sensitive to the quality of this developer-provided oracle. For the first research question then, our experimental study shows that CirFix is able to find plausible, that is, test bench adequate repairs to 21 out of the 32 defect scenarios. This is a repair rate of 65.5%. 16 of those repairs were actually found to be correct and high quality upon manual inspection, with the remaining 5 not as high quality in that they were overfitting to the test bench. The average wall clock time to find a repair was 2.05 hours, which is in line with previously reported behavior by successful APR approaches for software. But this really means that you generally want to leave CirFix running overnight as opposed to, say, over a lunch break to find a repair. And 7 out of the 21 minimized repairs were actually multi-edit repairs in that they required more than 1 changes to the circuit's design code to fix the bug. And while this is not a direct apples to apples comparison, CirFix's repair rate is actually fairly comparable to strong results reported by the software APR community, indicating that our approach is effective at, again, bringing over the benefits of software APR to this new hardware domain. Moving on to the second research question, we observed that CirFix repaired 12 out of 19 category 1 defects and then 9 out of 12 category 2 defects. The average wall clock time here to repair a category 1 easy defect was 1.9 hours, and that for a category 2 hard defect was 2.2 hours. And then we found no statistically significant difference in the amount of time to repair a category 1 versus a category 2 defect, suggesting that for bugs that CirFix is able to repair, it can do so in about the same time, regardless of the category and therefore the difficulty of the bug. For the third research question that we investigated, we found that CirFix fitness function is highly effective, again, as I hinted before, at capturing incremental changes to the circuit's design code to guide the search for repairs. In particular, we observed a high fitness distance correlation with our fitness function, a trait that makes genetic algorithms like CirFix thrive. A high fitness distance correlation essentially means that for each design, each edit to the circuit design that brings the circuit close to a repair, there is a corresponding significant spike in the maximum fitness individuals seen so far, and that's what we observed with our fitness function. We also noticed that our fitness function, in conjunction with our test bench instrumentation, is actually capable of increasing the testing prowess without any added or changed testing logic to the bench. Here on this slide, we have CirFix evaluating a candidate repair to a defect scenario to a project from OpenCourse. Notice how the original test bench reports no errors in the candidate repair, while the fitness function that CirFix uses reports a non-perfect fitness, indicating that a small part of the output by the candidate design is actually incorrect. But overall, we saw that our fitness function is a really good fit for this new domain. And then when it's paired with our novel fault localization approach, it is highly effective, highly successful at automatically finding and finding repairs to, say, defective hardware descriptions. All right, to sum it all up then. In this talk, I presented CirFix, a framework for automatically repairing defects in hardware designs with a 50% repair rate. The main contributions of our work include a new fitness function tailored to this new hardware domain. It's based on visibility and comparison. A new fault localization approach for hardware designs based on a fixed point analysis of assignments made within the design. And then finally, we also make available the first publicly available benchmark suite for defect scenarios for Verilog designs, for hopes that future program repair approaches can use this kind of a benchmark suite for their approaches, to evaluate their approaches. That is all I had planned for my talk. Thank you for your attention. And at this point, I would like to open up the floor for any questions you might have. Thank you again.